Welcome to homework.
Okay, this question is asking us about the identity of a compound with formula C, need a pencil there, C6H10O2. Now, as with many spectroscopy questions, a good place to start, in addition to the IR and HNMR information they gave us, is the formula itself. For example, we could determine the degree of unsaturation in this compound by taking the number of carbon atoms, number C, minus the number of hydrogen atoms divided by 2, as well as the number of nitrogen atoms or halogens, which in this case we don't have, and adding 1 to it to get our degree of unsaturation. And this tells us how many rings or double bonds we have. So in this case, we get 6 minus 10 over 2 plus 1 equals 2. So our degree of unsaturation is 2, which means we should expect 2 rings or 2 double bonds or a ring and a double bond right off the bat without looking at any of the information they gave us. Now we can follow this up with some of the information they did give us. The first bit of information we might look at is the IR spectrum. They tell us there's a strong absorption at 1,708 wave numbers. So somewhere in this region. Well, if we look at this chart here, which tells us where certain functional groups should appear in terms of wave numbers, we see that carbon doubly bound to oxygen should give us an absorption in that region. Furthermore, we have a single strong absorption at 1708 wave numbers, which suggests that we don't have multiple different carbonyl stretches or multiple different carbon-oxygen bonds, but that they are, if we do have 2, that they are identical and they would only give us a single stretch. That is, if we had a molecule that looked like this, because these 2 carbons aren't identical, we would actually see in our spectrum or our IR spectrum, we would see 2 peaks close to each other around 1700. Since we only see 1, we don't see 2 peaks, we just see 1 stretch, then that's telling us that it's very likely that we have 2 carbon-oxygen double bonds, but that they are somehow identical. This is likely due to symmetry. So we have some sort of hint that we've got a symmetric molecule with 2 carbonyls in it. That's what I'm thinking right now. But let's continue. Symmetric molecule, 2 carbons in it. Note that having 2 carbonyls would also explain our degree of unsaturation of being 2. So let's put down what we know so far. du equals 2, and it's likely due to 2 carbonyls and symmetry. Now, we've also been given some NMR information. We're told that there is a singlet at 2.67 ppm and a singlet at 2.15 ppm. Now, again, this is hinting at symmetry for me because we've got 10 protons, but only 2 signals, and they're both singlets. So there's not a lot of protons talking to each other, and all those protons are only giving 2 peaks. Once again, that suggests some level of symmetry, because when you have asymmetry, for example, if we had this molecule again, well, this is not a good example, but there we go. If we had the molecules similar to this with less symmetry, protons start talking to each other, and you start to get more proton signals. We've got 10 proton signals that are somehow only giving 10 protons that are somehow only giving us 2 signals. Now let's look at the NMR signal chart over here to see what kind of protons are these. So we're told that they're at 2.15 and 2.67. So we're talking somewhere in this region. What do we have in this region? Protons that are next to carbonyls. Well, that's a good sign since we would know we very likely have some carbonyls. We don't have any nitrogen. We don't have any halogens. It's possible we could have double bonds between carbons, but that's kind of counteracted by the fact that we're pretty certain we have two carbonyls. We don't have any triple bonds. So we can be fairly certain that our proton signals, or all the protons in our molecule, are due to protons being on carbons next to carbonyls. So let's just start messing around. We've got 6 carbons. We know that it's not likely to be cyclic, so maybe let's just look at linear. Okay. We could start throwing some carbonyls on here. Let's put one here and put one here. And we could just start doing a little guess and check, like, does this make sense for what our spectrum is? Well, we would indeed have protons that are next to carbonyls, but you quickly notice, oh, this hydrogen would not have the same signal as this hydrogen, and this side, we would expect 4 signals from this. That's not very likely. Let's try something else. You may already be seeing the answer, but let's try one more thing before we jump to it. This is how I would approach the problem. What about if we move that second carbonyl here? Okay, we have some protons there, and oh, no, we've run into a problem again because these protons aren't exactly the same as those protons. These protons would split these protons, so we wouldn't have just singlets. I'm going to move this carbonyl one more carbon down and see if that makes sense for what we have. Let's erase this carbonyl and move it down one more carbon. Okay, now let's look at this. We would have a couple protons here, a couple protons there, and 3 more here. Does this make sense with the information we have? Well, for one thing, we know that these protons, which I'll label A, are identical because of symmetry to these protons, which I can also label A. Now the same can be said for this set of protons. That is, the protons on this carbon and this carbon have identical electronic environments. They're both next to a carbon with 2 hydrogens, and they're both next to a carbonyl, and they're both of those carbonyls have a single methyl group coming off of it. So these protons are identical. Okay, so this is starting to make some sense. A singlet we would expect to be represented with an integral of 6 hydrogens for A. What kind of shape of peak would we expect for B? Well, since it's 4 identical hydrogens, there wouldn't be any splitting. Identical hydrogens don't split each other. So this would also be a singlet. And it would integrate to a height of 4. Well, they did tell us that the ratio between the singlets was 2 to 3. That makes sense with the ratio of 4 to 6. That's identical. These hydrogens are next to a carbonyl, so it makes sense that they would be somewhere around 2.6 or 2.15. Ditto for these hydrogens here. We've got 1, 2, 3, 4, 5, 6 carbons. We've got 10 hydrogens, 2 oxygens. Our degree of unsaturation is 2. We've got 2 carbonyls, but because of symmetry, they're identical, we do get our expected single carbonyl stretch in the IR. So this is our molecule. So we just stepped through based on degree of unsaturation, IR information, and NMR information to propose a few structures and find one that we could use to validate after checking all of the various variables that we get out of this molecule. So this, as for a name, this would be what hexane 2,5 dione.